hopefully the good one. Okay, cool. All right. Listen up, please. So can everyone give a warm welcome to Pash, who will be presenting first. Take it away, man.
So what I'll do is I'll just go through a bit of a recap on what you've learned so far, week 1 and 2, and just show you a bit of a glimpse into what the remaining weeks will be for materials. And we've got Will here, who will be helping to cover all of the calc stuff for the rest of the term. Okay. I've got an industry mentor here as well. So if you have any questions, please feel free to reach out to Will. Okay. All right. Let's just go through materials. Okay. And I'll try my best to highlight a couple of things. More so, not really to reteach certain things, but I'll just draw your attention to certain aspects which I think are really important. This will help your prep, because some of these things often get asked in quizzes and exams and stuff. Okay, so when we're discussing materials, the first thing we're looking at is what cement is made of. So cement production. Okay, so when you're looking at cement production, the main thing you have to remember is what the dry kiln process is. And it's going to look really annoying because I remember what the lecture slides looks like. It's just like a bunch of, there's a massive number of slides, each with like a lot of information about different aspects of the kiln process, right? And the temperature ranges and all that. Now, it's actually really important that you go through it and really have that information at the back of your fingertips, especially for, by the way, is the quiz open at all?
Yeah.
Is it open already? When is it due?
Next Friday.
Okay, you guys are all lucky. When I did the course, that exact same quiz that you're doing was a closed book test in person, and like we all got wrecked. It was like, yeah. So, and have you all already seen the quiz?
Yeah.
Yeah. See those true and false statements and all that? Yeah. Now that kind of questioning will be exactly what's similar to what you see in the final exam. Okay, because the final exam you will be tested on material stuff again, and that's kind of how it comes up. So dry kiln process is really important. A couple of things to be very clear on is the phases in the process. Okay, so all the different stages, if you recall, you've got the dehydration stage in the preheating tower, and then you've got the solid state reaction stage, etc., all the way and you get to the clinkering zone at the end, remember? You need to know very well what those processes are, is the first thing. The second thing you need to know are the temperature ranges. So at what temperatures each thing happens at. And the other thing that's important are your reactions at each stage. Okay, those are important. So for example, if someone were to say, let's recap it, not super seriously, but just to recap what some of these phases were. This is week 1 content, right? So let's first discuss the first phase. What's the first phase? In cement production. Yeah, you are raw materials. Put it in. It goes through a preheating tower into the preheating phase, right? Okay. For example, things to know off the top of your hand would be, for example, in the preheating phase, what are the chemical reactions that happen in the preheating phase? There's only one process that happens, which is decarbonation, right? So it's items like that to check off, like decarbonation starts to happen in the preheating phase. At which stage does alite form, at which stage does balite form, which one is more important for concrete strength, those kinds of things. That's the kind of questions that are asked, you know. So what the reactions are at each stage is really important to wrap your head around. Temperature ranges and the phases within the process. The other important thing is to know why dry kilns are more important. Well, why the dry kiln process is used compared to the wet process from previously. That was a tutorial question from last time. Anyway, and the other thing is your cement notation. And chemical formulas. That's the other important thing. Okay, so alite, balite, your ferrites, what those chemical formulas are in like normal chemistry, and your cement notation chemistry, like C3S and C2S and stuff like that. Okay, so those are really important to know. Okay, now there's week 2 stuff. Week 2 really talks about what happens after cement production. So remember, don't confuse week 1 with week 2, by the way. Week 1 stuff really is about how cement is produced. So how do you end up with your alite, balite, and all that other stuff, right? Once you have cement, when you mix that in with water, you will end up with paste. You mix it in with your aggregate, you get concrete. That is different. That's a process that comes after you produce the cement. So that is week 2 content, okay? So week 2 content is really about hydration. So this is concrete production, which means now that you have your cement, if you mix it in with water, you mix it in with the aggregate and all that stuff, you'll end up with concrete, okay? Important stuff to know about the hydration reaction. First thing is your chemical equations. Okay, for each phase of that hydration reaction, you really need to know it. The second thing is the heat evolution curve. You would see this, if I'm not wrong, in your quiz. It's a curve that looks like this. It's like heat, time, and it's basically a curve showing how the heat is given off when you create cement. Right, so you take your cement, sorry, not create cement, create concrete. So you take your cement, mix it in with water, what happens to the heat evolved? The curve kind of looks like this. Something like that. Okay? Now, the important thing about this curve is, this is your general curve, right? It's a curve that shows you the total amount of heat that's coming out. Okay, so this is your total heat curve. Okay, so it's important to know each aspect of the curve. That's in the lecture slides, right? Why is this starting very high and coming down? What causes this phase to happen? What causes this little kink to happen? Right? What happens at your final stage? Each of those phases that I've just highlighted, what happens here? Each of those things are in the lecture notes. It's really important to understand each part of this curve. Okay. The other thing to note is this is a total heat curve, which means it's the total heat that's given off from your cement once you mix it in with water. There are different versions of this curve. You have the C3S curve, you have the C2S curve, and you've got the C3A curve, so on and so forth. Okay. You have different curves with different heat evolution relationships. Okay. That if you sum these curves, you get the total. Okay, why is that important? It's important to know, for example, how the C3S curve is different from the C3A curve. Because what these curves tell you is what is the heat evolution of each cement mineral over time. Okay, and what this will also tell you is how certain things govern the behavior of this. So, for example, it's important to know that this spike in temperature here is caused by C3A. Not C3S or C2S or the other. This is caused by C3A. So this, in the C3A graph, you'll see that the heat thing spikes here, but for the others, not so much. Okay, that's what's causing this big bump, is C3A. And then when this comes down, and then you get this spike here, this is C3S causing this. This little kink here is caused by C3A reacting with foaming attringite. Okay. Again, all this stuff is in the lecture notes, but I'm just saying it's important to know those different aspects and understand that these curves have different versions depending on which mineral you're looking at. Okay, so heat equation, heat evolution curve is really important. Then the next thing is your water cement ratio. Importance of water cement ratio. That's really important to wrap your head around. What happens if you have a low water cement ratio? What happens if you have a high water cement ratio? How does that affect your strength? Okay, and then the other thing to also remember is how do you calculate your water cement ratio? How does that relate to surface moisture? So there's some calcs, they're really easy, those calc questions. There was a calc question in this week's shoot that had to do with water cement ratio. Super easy. That's kind of the I guess the difficulty of the questions that we're getting here. Okay. Tricky questions here would be along the lines of, so for example, a high water cement ratio in your mix causes low concrete strength in the final stages. Okay, that's something that's in the notes. But when you're curing your concrete, so we say you mix in your concrete, it's all mixed in inside, and now it's set, and now you're curing it, so you're spraying it down with water. If you spray it down continuously with water, does the strength decrease over time? No, it actually increases. See? So I'll say that again. In the mixing stage, if your water cement ratio is too high, the eventual strength of concrete drops. But once your initial concrete has set, if you dunk it in water, the water cement ratio doesn't go up, it stays the same. So it's actually better for your concrete. But you see, that might not have been mentioned outright in the lectures, like side by side. Although it's like part of the facts, right? It's in the lecture notes, but that's a trick question that can come up. Okay, is that does adding more water into concrete that's been set, would it increase your strength or decrease your strength later? It's a trick question because everyone will think, oh, he's referring to the water cement ratio, and then we'll say no. But that's not true. The answer is yes, it will increase your concrete strength because he's talking about curing. Those are the kinds of things I'm talking about. So it's like, it almost ends up being an English test really, where you're like, do you understand what the question was asked? But they're really just trying to test you those ways. So everything to do with water cement ratio, wrap your head around. The other thing to get good at is workability. Okay, what are the factors affecting workability? And what are the factors affecting curing, which is what I've just discussed. That's all the week 2 stuff. Okay? That's important. Now, moving on to week 3. The important stuff from week 3 is shrinkage. Okay? This topic is notorious because there's a lot of tricky questions that come up in terms of the different types of shrinkage. So for example, you have drying shrinkage and you have chemical shrinkage. Okay, you'll see when he goes through this in the lectures next week, right? You've got the different types of shrinkage, and within chemical shrinkage, you also have autogeneous shrinkage. Okay. The important part about this is there's another curve just like this that is usually tested. I've seen this very often. Under shrinkage, you have a curve that looks like this: volume reduction, okay, and time. Okay, and basically this curve shows you how does the volume of concrete change over time. So if this curve goes up, it means that there's more volume reduction, which means the volume is smaller. It's a bit of like a backwards way of, but you get the picture, right? So if this is higher, if there's more volume reduction, it means there's more shrinkage basically, right? And generally it looks like this. Something like that, okay? But there's different aspects to this curve. You can break this curve up into parts. between initial setting and after final set. Okay, I'm not going through this in detail, but I just want to bring this up to your attention. This graph is really important to wrap your head around. Okay, because there's a lot of trick questions they can ask about this graph in particular. Specifically to do with shrinkage, the kinds of questions they'll ask would be distinguishing between chemical shrinkage and autogeneous shrinkage. In fact, you'll see some of this in your true or false questions as well, if that's still being asked. Okay. Yeah, I'd say this is really important. Okay, I'll leave it there. Let's see what else. Okay, the other thing is this thing called SCMs, which is supplementary cementitious materials. Basically materials that will supplement cement, that you can swap out with cement. Why would you want to swap out cement? It's because the cement process, the hydration process, gives off a lot of carbon dioxide. Right? It's to decrease the carbon emissions from construction. In fact, there's a statistic out there that the construction industry is one of the largest emitters of greenhouse gases, right? Carbon dioxide being one of them. And it has to do with the carbon emissions related to creating your structural elements like steel and concrete. Steel is not really a problem, it's concrete. Concrete is the problem. Okay, because we don't use huge volumes of steel, but we use copious amounts of concrete, right? Because what's the maximum you can have for like a floor? You'll have steel beams running across, whereas oftentimes when people want to build a concrete floor, they'll come in and pour the entire slab, right? So because of that, what people are trying to do is trying to replace as much cement as they can, so that you don't give up a lot of carbon dioxide. So what does that mean? You can use supplementary cementitious materials. I'll give you some examples like silica fumes, slag, etc. Those are going to be in your lectures, in the lecture notes, but I'm highlighting it because that's an important thing to take note of as well. Okay, let me go through it. That is that, and then finally, I think the last part here to cover would be durability. AS3600 durability. Okay, so this is what you'll see in week 4, and this is a bit more calc stuff. So it's kind of like a soft launch for your week 5 to week 10 content. Okay, because it's still talking about materials. It's still theory heavy, but they're all calc questions. So what is this talking about? This is basically talking about if you're building a concrete structure out next to the beach somewhere, where it's constantly facing salt, right? The concrete will degrade quicker. So how do you choose a particular type of concrete that you're going to use so that it's more durable? Okay, so it's important. It's an important topic because this is when you start looking at AS3600. But by now, if you haven't already, I would recommend you jumping on to the UNSW library website, searching for Australian standards, and then follow that rabbit hole, and then end up with AS3600. Okay, it's an annoying rabbit hole, but look at that. And then download AS3600 and familiarize yourself with it. It's not too different from 4100 for all those of you who've done steels already, but just familiarize yourself with certain key important pages. I'll highlight now. Important pages in AS3600. Okay. The first one is your material properties page, specifically referring to F-C. F-C is your concrete strength. Okay, that's a really important page. You're going to be looking at it all the time. I recommend you find it and then just highlight that page. The next one is your beam design page. You're going to see this a lot, especially the page that have the formula for alpha 2 and gamma. I'm not going to touch what they are now, but you will need this for every design question. But it's annoying enough that, I don't know, even I haven't like actually properly memorized it yet. So like I'll still go and find it. Okay, so it's good to have the page with you, where to find this. Okay, alpha 2 and gamma. Beam design, and then it's good to have the column design page highlighted because it is in the course and it's commonly what is tested in the finals. Commonly, not every year, but there have been many years where he would your one of your design questions in the concrete final exam was like, how does it, like a column design question, okay, and then the other one would be a beam design question. Generally, that's what I've seen. Now, also pay attention to what he says in the last lecture or the second last lecture. Whenever he's talking about the final exam, towards the end, when the final exam has already been finalized and he's ready to go, he'll have a fresher memory of what's in the final exam all of a sudden, and certain things he might say in the exam would be a bit more important. Like I remember when I did the course before the finals, he straight up was like, "Oh yeah, the color interaction diagram is very important. you have to learn it." It was like, yeah, and then I went back and I told my friends, we're gonna like revise this together. Yeah, so column design, beam design, and see that's for the most part the introduction about the important stuff for AS3600. Of course, there'll be a couple of other pages that you need to take note of. As we go, you'll know. It'll be in the notes as well. That's your first 4 weeks.
You went over compressive durability and tensile durability as well, or like compressive strength and tensile strength. Is that in the material section or is that?
So spend a fair bit of time on it. There's 3 ways to test the tensile strength of concrete. The first way is called the direct tensile test. And the second way is splitting test. And the third way is the flexural tensile test. Okay, 3 ways to get your tensile strength of concrete. The first one is fairly obvious. You've got a piece of concrete, you grip it on either side with a clamp, and then you make it like that apart. Okay. The problems with this test: number one, the grip strength. Right? Imagine like you've got a piece of concrete that's very little like grip. If you get clamps and you grip it on the left and right, if you don't have enough gripping strength, the test will be failed, especially when something is sliding. If you grip it too hard, you might end up destroying the concrete. And also it's a dangerous test to do because concrete is a brittle material. So if you pull it apart and it suddenly splits, that's a big problem. Okay, that's the direct tensile test, but it'll give you the tensile strength of concrete directly. The splitting test is where you've got a cylinder that's lying on the ground, like that, right? So imagine this poking out of the board, right? And you've got a blade that's on top that's smashed through it, and you cause it to split. The way this is counterintuitive because people will say, wait, hang on, you're putting the concrete cylinder under compression, right? How does this give me the tensile strength? It's because if you have a blade like this with a sharp edge and you're slicing it through, it's inducing a stress that causes it to split, right? For it to split, there has to be a tensile stress pulling it apart that way. Okay? If you want to know exactly what the stress distribution looks like, if I sketch out the stress distribution, that's your straight line, right? Your profile. Let's say this side is compression, this side is tension. On the top side, it's compression, and the bottom side is compression. That's obvious because you've got that motion. But the stress you're inducing in the middle looks like this, sort of curved. Okay, so you're actually from like here to here, you're inducing tension. So you're not testing the whole cross section, but you're testing like a big chunk of it inside. Okay, so it's quite a preferred method to do it because it's safer. Yeah, and it's easier to do. Okay, that's a splitting test. The last test is the flexural tensile test. This is simple. Create a concrete beam, put it on your supports, and put a load on it until it breaks. Okay, there's 2 versions. There's this version. This is what you're talking about. There's this version, and there's this version. Okay? Let's say the loading on both of them is the same. The question now is which one is better? Okay? You remember?
Isn't it the left one?
This one's better?
Yeah.
Why?
Because for the 1 with 2 point loads, then the area that which can break is
Greater.
larger. Yeah.
Okay, so why is that a bad thing?
That part I didn't catch.
Anyone else?
I think it's because if there's like a big chunk.
So which one, the left one or the right one?
No, the right one's better. Because if in the left one there's like a big chunk in the middle, it might have like a higher tolerance, but that one has 2 points.
Very good, very good. The right one is more preferred. Okay, the reason is because of the bending moment diagram. So on the left, click red button. Right. The bending moment diagram for this beam on the left looks like this. Okay, which means the cross section that's experiencing the largest moment is only one cross section. This point in the middle. That's the only section you're testing. Is there? Okay, so it's rather unfair because if you have a freakishly strong cross section that just so happens to be in the center, what can cause that? Let's say you didn't spread your aggregate well enough, right? And all your rocks are all your aggregates all are clumped up here in the center, right? This will be very, very strong. And you're effectively only testing this cross section, so it's not fair, right? Because you're only testing one part. Over here, your bending moment diagram looks like this. It's preferred because you're testing a wider range of the beam. So basically, you're not only stressing one zone with the maximum moment is spread across your entire testing zone. So it's preferred, okay, in that sense. This is called a 4-point bending test. And this is a 3-point bending test. So preference is to the 4-point bending test. Now, the important part here is, how does this test get you the strength, the tensile strength of concrete? Because you're bending the concrete, right? How do you get the tensile strength of concrete? From here.
From the bottom side.
Very good. Very good. So the cross section, let's say it's a rectangular cross section, it looks like that, right? The stress distribution along the cross section, if you recall from Eng 2400 and the middle of steels, we did this, right? Compression on the top, tension on the bottom, this is the distribution, right? So if you know the total moment that you're applying on that part, you can easily solve what the tensile strength is. And if you apply the loads until something cracks at the bottom, the point at which it cracks is the maximum tensile strength of concrete, okay? But I want you to pause and look at this first. When you're doing these tests, you're only testing which fiber of the concrete. Only the bottom fiber gets tested, right? You're not testing the entire cross section. You're testing only the bottom part, okay? The other tests, at least they test the entire cross section, okay? All right. In the code, these are FT, and this is called FFT. Okay? Might be slightly different things. One's called FCT, etc. But the point here is the flexural tensile strength for concrete is different from the direct tensile strength or the splitting one. They will all give you different answers because of the different ways they test it. Okay? The important thing to remember about this is, what value do you use? They give you all of this in AS3600. What value do you use for beam design, you think? Because when you're doing beam design, you need to know what the maximum tensile strength is for concrete. But when you're doing beam design, which one do you think you should select? Sorry?
So whichever was the lowest.
Very good. Why? No, exactly. It's because we got this test result through beam bending. It's the most applicable, right? So just be careful when you're doing column design even, right? If you've got a long column and the column is going to buckle and snap on the tension side, when something buckles, it basically behaves like a beam, right? It'll bend like that. You'll have a compression side, you'll have a tension side. When the tension side splits, it's basically beam behavior. Okay, so even though in the code you'll have different types of tensile strengths, you will most of the time you will be using the flexural tensile strength, and you'll see there'll be a tiny subscript there that says FT. Okay, any questions? Yeah.
If the 4-point method is better because it like sort of tests more of the area, why isn't the loading applied even further apart? Just like one.
Because if you apply the loads further apart, your point loads need to be larger to compensate for that distance. Do you get what I mean? So for example, if your point loads are close, then for a small point load, you can generate a large moment. If you spread your point loads out, the bending moment in that range becomes smaller and smaller and smaller. So yes, you can, but you have to apply massive point loads near the ends to generate like a small even moment. So there is an optimization to that. Test methods, by the way, are standardized. Like at this stage, there are standards out there under the Australian standards that literally tells you if you're going to do a bending test, this is how long it needs to be, these are where your load needs to be, like it's standard, and then based on that you calculate it, and everyone will just believe you. Yeah.
Mike, can you test it with the UDL?
What's the problem with testing with the UDL?
Oh, doesn't that?
Yeah. Testing with the UDL is the same thing as testing it under one point load. It's not, you're not evenly spreading out the bending moment, right? Because what does a bending moment diagram with it for simply supporting UDL look like? Okay. You sure? Okay. Yeah. Any other questions? We're good? Alright, that's about it for materials. I'll hand over now to Will to take on with calculations.
Alright, I guess to introduce him, this is Will McCarthy. He's a graduate structural engineer at TGW. Yeah, let's give him a warm welcome.
The concrete structures course. So as you guys know, there's two parts to the course. You got the materials part, which is in the first 4 weeks, or you'd say, and then after that, you got all the calculation topics. So, and then when you have your final exam, it'll be broken into two parts as well. So you have part A, which is the materials part, and part B, which is the calculations part. So I'll be going through that. So cool.
Yeah.
Thank you. So, in terms of the topics for the calculation part of concrete, all you'll be looking at for the whole course, in this course, there's more concrete courses you can take as electives and stuff like that. But just for this course, there's only bending of beams, shear in beams, and deflection of beams, and also column design as well. So these are the main 4 topics which you have, and of course, at the start they cover reinforced concrete. In general as a whole at the very start. But yeah, these are the only 4 topics that you'll basically be looking at in this course. In terms of concrete, there's other stuff like slab design of walls, diaphragm, strut and tie. But yeah, those are the only 4 topics you'll be looking at. In this course, just make sure you have a copy of the Australian standards for concrete. It's really important. You'll be using that a lot. And if you go into industry as well, like that's the code you'll be using for concrete. It's a pretty big code. It's like, I don't know, 300 pages long or something. But yeah, you'll only be using like a portion of that, like for the course. Mostly like chapters 6, 8, 10, and 3 as well. And there's also a textbook, which I think Taiwan recommends as well. You don't have to use it, but it is a good textbook as well, so it's just there if you ever need it. Alright, we'll go to the next slide. Okay, so reinforced concrete. So when it comes to concrete, right, as we heard before, concrete is absolutely terrible in tension, but it's great in compression. And as you pointed out, it's 1/10, its capacity when it comes to tension. So in order to counteract that, we put steel, right? Steel will take all the tension for the concrete, and so that's why we put it. So I forgot next slide. Thank you. So yeah, we use steel, and We also use steel for concrete to enable a ductile failure mode. So when like a building collapses or something like that, it doesn't just fail in a brittle way, it doesn't collapse all of a sudden, it fails slowly, and you can tell like when a beam or a slab is sagging. That's why we also use steel, and also to help the control of cracking. When concrete cracks, it loses a lot of its strength, and you get fast crack propagation and all of that. And so in order to tie it back together, those portions that have cracked, we have steel there, and so that helps a lot as well. All right. So, when is concrete in tension? So, concrete in tension, right? You've got bending of beams and slabs, right? Which side is, so, okay, say I've got, what is positive bending? I might ask someone, what's positive bending? You know what positive bending is versus negative bending? No worries, that's all good. How do we find when, say I've got like a span, multiple spans of beams or slabs, how can we find which parts are in tension, which parts are in compression? Anyone have a clue? That's all right. So when we've got bending, right? Say I've got a beam that bends downwards like this. Which side is in tension? The bottom, right? Awesome. And when it's bending like this, like it's hogging. So this is sagging, right? Sagging. So we call these like over here. These are sagging moments because that's where the beam obviously sags. And over here where you've got negative bending. So this is positive bending, negative bending. And that's why in statics as well, you'll draw your bending moment diagrams like with the positive on the bottom and negative on the top. Do you guys remember that from 2303 for bending moment diagrams? And that's just to, resemble what the beam will look like when it sags as well, right? Because here, so that's positive, positive, negative, positive, right? You've got hogging over here, so it goes up like this. So negative bending is just defined as the top face being in tension, essentially, right? So,
sorry man, not to interrupt your thought, but I think some of the audience here, they've done solid mechanics. I don't think they've done 2303.
Oh, okay, no worries.
I think half of them might have done steels. So
cool.
Just
no
say
problem.
that.
Yeah, but really?
Yeah.
So actually, that's actually a good point. Has anyone like not done steels? It's totally fine if you haven't. Okay, great. Okay, we've got a few hands. That's good. So not done steels. What about 2303? Has anyone not done 2303? Cool. Okay. No, that's good to know. That's good to know. Okay. No worries then. All that really matters is when a beam bends downwards, the bottom face is in tension, right? Just like here, right? So that's where we're going to put the steel reinforcement, right? That's the main concept. When the beam bends the other way, right? When it hogs, when it goes upwards, the top face will be in tension. Does that make sense? Is anyone not too sure about that? Cool. So basically, wherever there's tension in the beam or the slab, that's where we put the steel reinforcement. Is anyone unclear about that or have any questions about that? Because that, to be honest, is like the main concept of all this, especially for electrical analysis. Anyway, I'll keep going. Great thing. So, as I know you're all getting started for this, and this is a crash course, so just wanted to start off with some terms to help you get familiar with, right? So, like, for example, a typical concrete structure. So some terms, you've got a slab here with gravity loads acting down on it, just like you would in a building or any structure really. You've got slab, columns. You might have beams running on the outside or underneath this slab, right, to support that. And then under that you have footings which will then take it down to the ground. So all the loads basically travel, span this way or span that way, span out and then down and always down to the ground, right? Okay, and then over here, got like what a typical concrete section might look like, and this was stolen from Crash's notes, which are really good. So yeah, copyright to him. But this is what a typical cross section might look like for an RC beam, reinforced concrete beam, right? longitudinal steel on the bottom, right? And that's that steel which is on the bottom from the bending, right? And that's taking all the tension. So that's why we have lots of steel on the bottom. Not as much on the top. Sometimes no steel on the top. Technically in standards, like you always have to have steel there. But basically, you look at in the course like singly reinforced concrete beams, which is just like having a cross section like this, where you just have steel reinforcement there. And you'll look at this in theory and all that, right? But we just need to put steel up here in the real world just to control cracking and all different types of failure modes as well. So some terms to get familiar with, you've got cover. So Prash talked a bit before about durability in concrete beams, right? So in order to protect steel, right, because steel rusts, right? When it's near the ocean or where there's lots of wind, lots of moisture, steel rusts. So in order to prevent that, we just basically provide concrete there. If we, wanted to, we could have steel all the way down here, and that would be like the most optimal because, as the furthest fiber in tension is going to have the most tension. But we can't do that because otherwise the steel will just rust. So in order to prevent that, we provide cover. And when it says clear cover, that's just like the absolute cover that you have there between like the bottom of the section and then to the bottom of the rebar. You also hear just cover by itself, and that just like refers to the outermost section to like the central of the rebar. Other words for steel reinforcement are like rebar, Rio, which you might have all heard before. And then we've also got, so that's longitudinal reinforcement into the page, so that's taking all the tension. And then the other main thing which he saw before was shear in concrete beams, right? So in order to take the shear in a concrete beam, we use stirrups. So these over here, right? And I'll show you a bit later how and why that's the case. But just so you know, those stirrups are also used to take tension in concrete. And that's what I wanted to cover there. So if I could just go to the right a little bit. This one? Yep, that's great. So, that's it. No worries. That's it. And then another main thing, when we look at reinforcement in concrete, in order to engage that reinforcement, so I could have a concrete beam, right, like this, and say it's supported over here, right? I could have tension down here. I put my rebar down here because it bends like this. But if I bend this beam and it sags, this is all going to be in tension, but in order to make sure that it's all engaged, I need to collet or hook the rebar. So those are just other terms which you'll see throughout the course as well. Yeah, it's just to basically engage that and make sure that it actually works. Because if you just have it leaving off a little bit there, then this part which is in, this part which is in tension is just like not going to do anything. Yeah. Anyway, so cogs, hooks, yeah, other terms to get familiar with, as well as lapping. So lapping of bars, because if I've got a say a concrete beam or span like this, we talked about before, right? This would be in tension. This up here would be in tension. Like if this beam is bending, it's going to look like that sort of. Like when this sags, when it deforms, this is going to go down. This part will go up, etc. So put tension bars. Sorry. In order to take that tension. But in order to engage it all the way, like we did over here, by hogging or hooking the bars, we make sure that we, they overlap in order to take that tension. Or if I'm using multiple bars and like this, and I want to make sure that all that tension is being taken, I need to overlap these parts in order to engage them. That's all. All right. Next one.
Which one do you want to do first?
Yeah, so just some more terms as well. As we talked about, stirrups, hooks, different types of beams. You've got T-sections, just regular rectangular sections, band beams. Anyone know where you might see band beams? Anyone want to have a guess?
Bridges?
Bridges? Not quite. Good guess. Like, it looks a lot like a bridge girder. It does, yeah. I totally get what you mean. It very much looks like a bridge girder, but still in a bridge. Might come over here. Would be, more like this. Like these are more your beams, or if you have, like a girder like this, it kind of behaves a little bit differently. But that's a really good guess. Can you think of maybe anywhere else where you might see band beams? I'll give you a hint. Think about like where you might need to, like if you've got a floor and you want to really have the most head height as possible. So ceilings, they're, like sort of ceilings, yeah, but like what type of place would you have those? Yeah, say you want... Alright, I'll just spill it. But basically, car parks, right? In car parks, you might have seen these a lot because they need as much head height as possible for vehicles, right? You know what I mean? Yeah.
Talking about the well-built ones.
Certainly I have the rubber. Because say I have a concrete section, right? Okay, say I load both these sections on the top with a UDL. So imagine it's just like running into the page. Does that make sense? It's like these beams, they come out of the page and they've got a UDL on top of them. Which beam is going to be better? Which one's more likely to stand up or stay standing? Left one? Why is that?
Wait, to stand up?
Like basically which beam is like going to be best? Like if I, say you were like, I don't know, walking across a river or something and you had like a plank, which way is better? And it's like, or say like a, I don't know, like a box section like this. Is it better to lay it this way, or is it better to lay it this way? Which way would be stronger?
I think the left one, but it has more bending resistance.
Why does it have more bending resistance?
Because it has more volume, more.
Say these like have the same like area,
Oh.
right? Like this is the same thing, but this is just rotated 90 degrees.
It's because when the axis of the pressure being applied onto it. So if it was, so to say like if you were compressing, if there was a point coming from the x-axis on the right hand, then it would be stronger than if you were to stand.
That's right. So if you applied that in that direction, this would be stronger in that direction. That's right. So essentially, this one's better, right?
Mm-hmm.
But why is it better?
Is it because of the cross section? It's more on top.
That's right. It is because of the cross section.
3/4 better or something.
The top bottom surfaces are further away from the center point.
Perfect. Very well done. Nice work. Exactly right. This one.
That's exactly what I said.
Does anyone know the formula? That's it, yeah.
Always the moment of inertia.
That's exactly right. Moment of inertia, right? Which is B d cubed on 12, right? In this case, B is this and D is this, right? In this case, this one's B and this one's D. So notice how this one, you have a lot more height, right? So when you cube this one's going to be a lot better, right? And where you use this, right, is you use this in your deflection formulas. I'm not sure, where everyone's at with that, but if you remember, like going back to statics and all that, or maybe mechanics of solids, you might have seen this formula, right? And yeah, so basically, the larger your I value is, the less your beam is going to deflect, and that's basically it. Same goes for like when you have stress as well, which you might have seen from mechanics of solids. Z is equal to I over y, and yeah. Anyway, that's enough of that. In concrete design, there's also things such as slabs, and you've got one-way slabs and two-way slabs. You won't have to deal with that too much, but it's just more notation and more terms to get familiar with. Go to the next. Sorry. Thank you.
Oh, yeah, so most of them haven't done steels.
Cool, no worries.
The stuff that you did last time.
Yeah, sounds good. So just another quick show of hands, just real quick. Who has done steels? Cool. Okay. So just a few of you. So this will be your first time getting to know limit state design. Now it's nothing too complicated. Basically, all it is like in real life, like as engineers, when we actually design structures, all we're basically doing is using this principle the whole time, right? And all it's basically saying is like, say I want to design a beam, right? And that's totally fine. Yeah. Say I want to design a beam for someone. Let's say someone's standing on the beam, right? Let's say they're like, say 100 kilos, right? I'm not going to design the beam to withstand someone who weighs 100 kilos. I'm going to design the beam to withstand someone who weighs 120 kilos, right? Because I don't want it to fall down. This is basically all that is, right? It's basically saying whatever you design for, you want to make sure that it's always bigger than the things that are going to be applied to it, the loads that are going to be applied to it. So that's literally all that is, all that means. Limit state design. So basically, and this is basically the main concept of all of concrete and steel design, right? This is your design, like action effect. Basically just means like the loads that you want to put on it in the future. So say you design like a hospital, right? It might have loads from equipment, machinery, just people walking around the hospital. And so basically what you're going to do is you're going to make this seem a lot worse than it actually is. So you might apply factors of like 1.5 or 1.35 over here, right? But when you're actually looking at the beam that you're going to design, and because it's all theoretical, we don't live in a perfect world where we can design everything that like down to the, very last atom. We got to actually be realistic about it. So these numbers over here, when we actually look at the beam, we're just going to pretend it's like a lot worse than it actually is. So on this side, we're going to apply factors like 0.9 or 0.85. And that's all limit state design means. Basically, you take whatever you want to design, say it's like a hospital, and you got all these loads on it, you make them seem a lot worse than they're actually going to be, right? And then the concrete like design section that you submit, as an engineer, you basically make it seem a lot like worse when it actually is. Is anyone not too sure about that? That might not have been the best explanation. I can explain it in a different way.
Does a lower number mean stronger?
So, lower number means stronger. So, what do you mean by that?
0.9 is lower than 1.5.
Yeah, so, like, basically, what I should do is I should write.
Just highlight these ones.
This is like your. This is like the section you design. So say like you design a concrete section and it can take, say, 20 kilonewtons, right? You get that from all your theory, all your notes that you've done, right? But you're going to make it seem worse than it actually is, so that it can like theoretically take more loads. So you're going to like reduce this down, okay? Now say like the loads you have, say you're designing for someone who weighs or let's say it's a car, right? Car which is 10 kilonewtons, right? Like 1 ton, 10 kilonewtons, right? You're going to exaggerate that and you're going to make that seem a lot worse than it actually is. So over here, you're going to apply like 1.5.
Okay.
Does that make sense?
Yeah.
Cool. So like the beam you design, you use like all your theory, all your notes from Concrete 3304, or you use like all your, all the software, and you design your section and it spits out a number, say 20 kilonewtons, but you make that seem worse, just in case like this is really close to being 20 kilonewtons, right? Does that make sense? Does anyone still like not sure? It's totally fine if you are. I'm happy to explain like it again for 100 times because this is really, really important. If you're still unsure, we can talk about it afterwards and we can go through it again. But yeah, this is all about limit state design. So whenever you're designing, we call it ultimate limit state. That's for strength. So we use all these factors and stuff like that. When we're designing for serviceability, or like when a beam, and serviceability just means like how, when you're like, when it's in service. It's like, for example, this room, like we can walk around this room, we can, stand around, walk around. That's like, the room is like, providing its service, right? But if we're walking around and like the slab's like moving up and down, it's like, resonating, it's vibrating, it's sagging when we're walking around, then it's not serviceable. But it's still standing up, but it's not serviceable. So that's like deflection. And so then when we use we don't use these like big factors to factor everything up and down. We use like more realistic factors. So, we actually just take the loads as they are and don't apply these like 1.5 because they're not as important. The beam, like the room deflecting, is not as important as the room falling beneath our feet, if that makes sense. Anyway, sorry.
Sorry, Matt, do you reckon? So I'll hijack the slide slightly just to highlight the ones that are important for.
Oh yeah, cool. Yeah, perfect. Thank you for doing that. Yeah, that's great. These are basically like the only 2 load combinations that you'll use in this course. So to be honest, like I wouldn't even worry about like all this stuff. I don't recall like table one using any of these ones here. Don't worry about it. Like you'll use them maybe in industry later. This one's important for other stuff, but you don't have like uplift when it comes to deep concrete slabs as much. And then these like all your serviceability ones. So see how like the serviceability ones, we don't apply these like factors the same way, okay? Because we can take a more realistic approach. Remember, the room deflecting is not as important as the room falling beneath us, so we can be a bit more realistic about it. Okay.
Do you reckon it's worth running over what the difference between G and Q is?
Yeah, for sure. So G just means like your dead load. Like think like gravity, like just if you have the building there, it's just that's your G. Q is just your live load. And what's live load? Anyone know what live load is?
Whatever the top of it. Like in that example being a car.
That's good, yeah. Car would be a good example of live load. But say you had a museum, right? And you had cars like in the museum. Would they be live load or dead load?
Like, are they parked or are they
Parked, yeah.
They'll be dead.
Yeah, dead load, because they're just always going to be there. They're like a superimposed dead load. Like you design the structure, right? You got the structure itself, which is a dead load, like all that weight of concrete, and then you're also putting stuff into the structure. So that's also dead load. But then live load is stuff that might come in or out of the structure. So for example, people, right? That's your Q. So you got G, which is dead load, so just everything staying still basically, not moving, and then live load. Live load is like people, cars going over a bridge. Yeah, like mostly people, to be honest. That's mostly like your live load, like in most cases. But they can be like all kinds of different loads. Animals, literally, like cattle, stuff like that. They're examples of live load. But So yeah, so this is really important, but yeah, you'll mostly, in fact, you'll like only be using these load combinations and these ones. Yeah. But if you're not too sure about it, we can definitely talk about it like afterwards as well. But yeah, it's quite important. This is called limit state design. Your ultimate limit state, which is your strength, and then your serviceability limit state, which is like your deflection. Alright, should we go next one? Cool. Yep, awesome. So like we talked about for concrete, right? In this course, you will only really be looking at like two main failure modes for concrete, which is just concrete bending, like flexure, so like cracking here. And then the only other one you'll be looking at is shear, which is just over here. This is literally like the only two things you'll be looking at in terms of strength for concrete in this course. So the first one we'll look at is this portion here, flexural analysis. So beam, slab, bending, and then you get cracking in the middle, right? So when this beam bends, this portion is in tension. And remember, concrete is like really crap in tension, so it's just going to crack from the bottom, and then the tension is going to be taken by the steel. Right? So let's next one. Yep. Yes. Thank you. Okay. So this is like what I was talking about before, right? When you have concrete beams, we reinforce them to take that tension. The first thing you'll like cover in the calc course is like looking at singly reinforced beams, which is just having like the steel in the most important part, which is in that like bottom flange or bottom area of the beam, and so that's the most important steel really. So you'll look at that, you'll like do some calcs in class. They'll be in your workshops and the assignments, stuff like that, and the main thing like you'll be doing for the first week or so is looking at like going back. Actually, just quickly, show of hands, how many people have done 2400 mechanics and solids? Has everyone? Some people haven't done 2400. Cool, no worries. So all the formulas, like they'll give you all the formulas, so it doesn't matter anyway. But if you remember from 2400, when you have composite sections, do you remember like they, like transform sections, like you make the area seem bigger for like different materials. So like, this, steel, right? It's got a larger yield stress. So, you can, like essentially the equivalent of this in concrete would be like a lot more area, if that makes sense. But yeah, they have all the formulas, and you just go through them. Taylor will, guide you through those. And you'll start off with singly reinforced beams, and then later on you'll just do doubly reinforced beams, which is pretty much just the same. And by the way, what I was referring to before is that transformed section stuff is like when you have, different material like steel in here, and then instead of like imagining it's concrete and steel, you just imagine it's like all concrete, and so like you extend the area out here. Like this basically, this beam with steel is equal to like this beam just made of concrete. Does that make sense? Cool. So yeah, that's that. And then likewise, if you have, so that's like a singly reinforced beam. If you have doubly reinforced, it's just like the same thing. And then you just follow very similar equations, which like, really aren't too difficult. Like, take one, will derive them all. You don't even have to like memorize most of them, to be honest. Because in the exam, when you do your flexural analysis, your shear analysis, you'll just be like going through step by step. The steps for those analyses, and you don't actually have to worry about these so much because they're already basically derived in the code, in the Australian Standards Code, which is also here, by the way. If anyone wants to have a look afterwards, just got a copy there. But yeah, anyway, I'll go to the next slide. Yeah, thank you. And then the next thing that Taylor will go through will be the stages of reinforced concrete beams in bending. And this part is quite important because it really talks about how what goes on when a beam bends. Yeah. So when a concrete beam bends, right? Say you got a concrete beam, no load on it. You start to load it, right? It starts to sag, starts to deflect, starts to take some stress. You got the first stage where the concrete hasn't cracked at all, right? Just the same as it was before, hasn't cracked yet, no cracking. Tension's not great enough to crack the concrete just yet. But then as soon as the tension in the bottom becomes too much from bending, then the concrete will start to crack, right? Because there's a very poor tensile strength, like we said before. It's 1/10 of its compressive strength. So as soon as it gets too much, it'll start to crack. And those cracks will start to move up the section. So if I've got, this beam, and you start to get cracks here, it'll start to move up the section, right? And then, so that's still the elastic stage. And then basically, you've got stage 3, where the concrete has cracked, and basically, the concrete offers no tensile support whatsoever. So basically, your section, I might just rub this off. Basically, your section of concrete has cracked up to here, and you've got your steel down here essentially. You may as well not have any concrete there. That's just pretty much how it behaves. Because all this concrete that was there before has cracked, and it's basically useless at that point. This concrete is in compression, and the steel's taking all the tension. And that's the third stage of when a RC beam bends, when it goes through flexion, essentially. So, next page. Yep, thank you. Yeah, cool. And you can see these different stages here. So your stress and your strain is elastic. It's all linear. There's elastic stress strain profiles for the section, and then when you've got the go to the second stage. By the way, these formulas, Taylor will go through all of these as well, which you'll learn. It's just like derivations. You don't have to memorize them or anything like that. I was going to say something like that.
You want me to go to the second stage? Or is it part of this?
This one.
Yeah, sure.
Yeah, cool. So in the second stage, right, the concrete starts to crack, right? Now, when you do your calculations, right, before the section is cracked, okay, let's say I got this concrete beam, right? There's no reinforcement in it. Where's the neutral axis? The middle, right? Perfect. That's exactly right, the middle. Right? Because it's a symmetrical section, rectangular section. Now let's say I put steel in here. Where do you think the neutral axis will go now? Shifts down? Why?
Because there's more forces are more towards the bottom. There's tension and pressure.
Yeah, that's pretty much there. Yeah, that's really good. And were you gonna add something there?
Oh, was it because of the, when you change the steel, then it gets larger because of the...
That's exactly right. Yeah, both of those answers are perfect. You may as well look at the transform section, right? Transform section would look like this. So technically, right, it may as well be a whole section of concrete looking like this, and you've got more area down here, right? So your neutral axis will shift downwards, right? Now in the third stage, right? Draw this. Got your steel, right?
Do you want me to go to the third stage on the slides?
Yeah.
Yeah.
Thank you. Third stage, your concrete cracks. So all this basically goes, right? And it's basically all up here now. When you go from this stage to this stage, does your neutral axis keep moving downwards or does it go upwards? Why?
Because there's not any more mass at the bottom to like for the neutral axis to
Yeah, that'd be exactly right, right? It's basically like all about the area, right? So if you put more area down here, neutral axis is going to shift down here. If you have less area down here now, neutral axis will shift. Nice. So then, when we do this, right, we have no concrete here, right? The concrete may as well be useless because it's just like so far gone, can't take any tension, it's not doing anything. This part is still in compression mode, right? Because it's just like that when that beam was sagging before. Tension in the bottom, compression in the top, right? So when you draw the stress strain profile, it's not going to be elastic. It's not going to be linear. You're going to have this weird looking stress strain, stress profile, right? That looks something like this. And multiple tests have been done on this, experiments done with this, and what you get here is this sort of weird looking curvature when you look at the stress in the concrete profile. So this is what it really looks like. But in order to make it simplified, in order to simplify it, because we don't really want to work with this, it's just too messy, we basically just turn it into a nice rectangle. So you got the concrete in compression and the steel in tension. So you basically got like the stress block versus this like sort of point force, because the Rio is just like, you know, very thin. So that's what it looks like. Does that make sense? Is anyone not too sure about that? Cool. And there's a name for this. We call this the Whitney stress block, which Taewon will go through as well a lot in detail. So basically, when we design a concrete section, right, we got this in compression and this in tension. So when we look at the bending capacity of a beam, we basically just got this force couple, right? Moment couple. So basically, if we were to look at the, yeah, perfect.
Do you want that one?
Yeah, sure, that'd be great, thank you. And this is your main formula. So this is the formula that you'll be designing to when you do your exams, when you do your quizzes, right? This is like the formula for flexural analysis. It's really like, obviously you have to derive all these terms or not derive them, but you have to get the terms and plug them into the formula. But this is the main formula that is used to just assess the concrete beam for bending, right? Now, if you have a look at this, it might look a bit weird at first, because I know you, like a lot of you guys haven't done steels yet, haven't done limited state design, but it's actually a lot simpler than it looks. Basically, all it's doing is going back to that section where we had.
I'll just put it up as well, yeah.
Oh, thank you so much. Basically, where we have this section, right? Got this force couple. So if we want to look at the moment capacity, all we do is I like to use, when you look at stress, it's like M on R. I've seen the best way to explain this. So forces is M on R. But basically, you know, at like a moment, right? It's basically just force times lever arm. isn't it? Right. So say R is my leveron. Let's just call that R. No reason for calling it R, just R. The moment generated by that is just going to be the forces. So like this is, actually I'll draw it here. This is tension, right? And if I make a resultant force of this stress block, right? Like UDL resultant is just halfway, right? Then I can call this compression, right? So the moment there is just going to be the force times the leveron. So the moment is, say for example, T times R, right? That's all it is. Or C times R. Doesn't matter which one you choose, but it's just force times leveron. That's all it is. So the force in this steel, right? If you guys remember, force or stress is equal to force over area, and so then force is equal to stress times area. So if I'm looking at this steel, right? And I want to get the force, well, it's just going to be the stress times the area. And if I'm looking at the capacity of this concrete section, I'm going to be looking at the yield stress of the steel, right? So in this case, it's going to be FSY, which is just the yield stress of steel. Don't worry about the notation so much, times by the amount of steel that's in there, which we call AST. That's all that is, right? So that's the force going through there. And then you just got to work out the leveron, right? Now, Taewon will go through this as well, but the lever arm is just the distance. You can, because this will be the top of your concrete section here. This is like the bottom, or this is the bottom because you got cover, right? This distance is called D, which is your depth to reinforcement, right? And the depth to this, resultant force halfway. Well, the depth of this stress block is gamma dn, which you go through the theory in class. So don't worry about that. Like, it won't make sense right now, but you'll go through the theory in class. But basically, this distance is gamma dn. So if you look at halfway, right? Halfway would just be gamma dn on 2, right? So your distance between these two things right here is just d minus gamma dn on 2. So when you get your moment, right, your moment is just going to be force times leveron, so to speak, FSY AST times by the leveron, d minus gamma dn on 2. Does that make sense? Anyone not too sure about that? Any questions or anything? Sweet. So that's basically like your moment capacity. That's how much capacity you have in your concrete section. Anytime you design a beam, that's all it is. That's all you're looking at. Now, remember from before when we talked about limit state design, we want to make the section seem worse than it really is. So all we really do is we just apply like 0.9 to this, or actually from the code, I think it should be 0.85. Yeah. So we 0.85 times this. And that's just your phi factor. That's what that phi symbol there looks like. And you'll see the U subscript, MU, that just means your ultimate moment. So when we talk about ultimate limit state, ultimate strength, it's just like when the beam will absolutely collapse, absolutely fail, can't use it anymore. So that's the ultimate capacity. And you're comparing that again with your M star. So like you take your, all good if I rub this off. Does anyone need this? Cool. Oh, yeah. Sweet. Yeah, that's right. When you take your beam, oh yeah.
I think I really got that.
When you take your beam and it's got like some UDL on it, right? Say it's like 5 kilonewton meters, 5 kilonewtons per meter. Does anyone know what M star is for simply supported beam? From your statics or anything like that?
Were you guys in precious class?
Or if not. The moment at the middle will just be. Also? W L squared on A. That's what it is. You should actually familiarize yourself with this like simple formula. It like comes up a lot, and you use it a lot for simply supported beams. So I would actually like memorize this. I mean, it's not too bad to memorize. But yeah. And then when you use your M star, instead of taking like 5 kilonewtons per meter, say like, you know, that's like people walking across a bridge or something like that, you make it seem a lot worse. So you times this like, say, for example, by 1.5 or 1.35 for dead load. Let's say it's like live load, then you times it by 1.5, you plug that in, and then that would be like your left-hand side of the equation. Yeah. Anyone have questions about, so that's flexural analysis. That's all beams bending, right? So that's like the first check you have for checking concrete strength, beam strength.
Guess which week we're up to, guys?
5.
5.
But honestly, I mean, like, I honestly wouldn't stress too much. I know that seems really bad, week 5, but you know, after that you have week 6. You know, obviously great. But the only other things you cover are literally just shear, deflection, and column design after that. Like those are the 3 main topics. And like if you understand those topics and you have a good set of notes from Prash, when you do your exam questions, it's actually really easy. Like it's actually a lot easier than it looks. You just have like those 4 main topics in the calculation part, and then you're set.
Yeah. Did you want me to show a particular slide when you were talking there? Sorry.
What's that? Oh yeah, like in fact, yeah.
Oh, do you want to talk
okay,
about
so I'll come back to the final exam now if you want.
Yeah.
So like this is an example of a final exam, right? You got part A. So this is part A. Both these pages, and that just goes through the chemistry side of things, the material side of things. And obviously you might have different questions, not always like this. But yeah, that's the material side.
Next one.
And we'll go.
Oh yeah, those are just solutions as well. Oh right, for the material stuff. Nice.
Yep. So that's
Thank you.
the solutions for the materials, and then you have this. Now, it looks like there's a lot going on. I know there's a lot of notation and stuff like that. But seriously, it's like when you have a set of notes and you can go through it step by step. A lot of the notes in this course are just like step by step, so you don't have to worry too much. Taewoon and Kim doesn't throw like too many curveballs. So as long as you have like a good like sort of flow chart or step-by-step process of how to just answer these questions, then like honestly it's fine. Is it alright if you just go back to the first calc question?
Yeah, bro. This one.
Yep.
Is that right? Oh no, sorry. The actual question.
Thank you so much.
Yeah.
So for example, this question is just testing the bending moment capacity, like the bending, flexural, which we just went through. And we just went through like the main part, like going back to that formula, like all this work is just to work out that like main formula. Like if you understand like the concept, understanding the concept behind it is a lot more important than like having the notes. Like the other way around, it's just a lot harder. But if you understand like what's going on, like the notes will be a breeze, honestly. It's just like a step-by-step process. So that's bending. That's the first calc question, and then
The next one.
yeah, and then the next
Two
calc
long
question,
calcs. Yeah.
The next calc question will be shear. So you got bending first, and then shear. So this question is all about shear. Shear reinforcement, transverse shear reinforcement, develop a shear force envelope. Yeah. By the way, shear force envelope. You know when like you got your super supported beam, and you draw your shear force diagram, which will look, something like that, right? When you draw your shear force diagram, all the shear force envelope, when it says shear force envelope, all that really means is taking the value over here. Because when you have like concrete columns, like this, the shear force, you're not interested in the shear force so much here because there's a column here. You're interested in the shear force, that's happening right here at this point, or technically at an angle. So you basically take this distance d away from center of the column. So when you do your shear envelope, you're just getting that. That's all that means. Whenever it says shear force. And then the last question. So is there right to go to the last one?
Is it 3 long calcs?
Yeah, this one. Yeah.
I think
So some exams will be different. Well, obviously they're all different. The past exams. The last one here, I think, goes through. Yeah. So this is a deflection one. So in this exam, there was bending, shear, and deflection. Right? In a lot of past exams, I've seen like this being columns, right? So it might be that instead, or it could be like all 4, and then like these last 2 are like really short or something. You know what I mean? But again, these are the only 4 topics you have to worry about in this course. Yeah, and that was the last calc question.
Yeah, I see. Is there much else in there? I'll just quickly. Sorry.
Yeah, for concrete columns, it's not too much. You just have like an interaction diagram. You look at like just axial force and also bending. Yeah. I'll just ask one quick question, and then it might go on a bit. Yeah, I'll probably wrap it up on this question. But let's say you got a concrete column, right? When you design concrete columns, you got this really high force over here, right? So this is your axial force. This is your bending moment that a concrete column can take. Why is there no diagram down here? Does anyone know? Why can't it go negative? The axial load, what about it? Why?
Because it cannot experience tension.
Nice, very good. That's right. Concrete column can't experience tension, it can only experience compression. So that's why all your values are positive for axial load, right? Steel, you can look in compression or tension, doesn't matter, right? But for concrete, just looking at compression load. And you got your moment over here, right? So concrete columns can only take obviously a certain amount of moment by themselves. But then the diagram starts to sort of shoot out in this direction, right? A lot of interaction diagrams you see, like, when it comes to design of certain materials or, like, in fact, columns for different materials, a lot of the time the interaction diagram will look like this. It'll just be a triangle, right? And you can only stay within that triangle. How come for concrete columns, or columns in general, when you have moment, you can get more moment capacity when you increase the axial load? Why?
That's just a guess. Is that because it also counts the weight of the actual column itself? And it's kind of collapsing. So the bottom takes the load from the top of the column and what that's on top of it?
That's. I feel like you're quite close, but it's not quite. But do you want to elaborate a bit more?
Well, my brain is just thinking like,
Yeah.
so if a column has a load on top of it, then it would usually bend that, right?
Yep.
But like it also has the weight of the column itself. So the bottom is also taking the weight of the top like portions of the column. So that would take more bending into it.
I feel like. So you're saying like because of the weight of the column, like there's more weight at the bottom,
Yeah, it's
then
like
there's more
gravitational
capacity. That's true. That's spot on. That is right. Like if you have a concrete column, technically there'll be more compressive force at the bottom. So technically there will be more capacity. But what actually is the reason behind that? So you've got a column, right? And it's like bending like this, right? But now I'm saying that if the columns are say bending, and I apply some axial force, it's actually going to be stronger. Why will it be stronger? So if I bend the column, if the column just bends like this, right, it'll break at like a certain amount, right? But if I take that same column and I apply compressive force, it's going to get stronger. Why?
This is just a guess. Is it because you put slightly more of the concrete into compression where it becomes stronger?
Very nice, that's exactly right. So you have this column, right, that's bending, it's like a, it's like a beam, rotated 90 degrees, right? One side of the concrete is in compression, one is in tension. But when you apply an axial force, right, you induce more compression on that tension side, so the tension is reduced. So essentially and because concrete is so great in compression, basically just make it stronger, because you don't have to worry about that tension so much anymore. So yeah, that's what check it out. Yeah, I think I might leave it at that, because it is going to be over time.
Cool.
I'll just a word of advice for when you're revising for concrete and you're studying for it. The week 5 stuff, all the stress stuff that Will went through earlier, when Taewon does do it in the lectures, trust me, the first time you do it, it's going to be pretty confusing, right? What some students tend to do is they will skip over it and try their best to memorize the formulas that come out of that. I wouldn't recommend doing that, because if he does change something in the cross-section layout, none of those formulas that you memorized are valid. Okay, so the hardest, to me, I think the most challenging part of the entire course is that week 5, understanding the stress diagram. If you understand how to draw it, you don't have to memorize it, but if you understand how to draw it, you can derive any formula you want for the rest of the course. And it'll keep coming up over and over again. Unfortunately, it's not like steels. Steels you've got 50 formulas or something, and as long as they are put in a mind map, you can find your way around. Just as concrete can be anything. You put an infinite number, an infinite number of possibilities for how big your cross section is going to be, how many bars you're going to use, what strength you're going to use, etc. The final answer will always be different. So just spend a bit of time in week 5 and don't get scared about the stress diagrams. You'll get it eventually. Once you pass that, it's all easier from there. And the other thing I wanted to add for materials, which I forgot. This is an exam question that I got when I did the exam. It hasn't come up. It's only come up one more time since I did it. So it seems ripe for recycling. So just keep in mind, the question I got was regarding it was like a scan that showed something microscopic. You couldn't tell anyway. I did it on piece of on pen and paper, when I did the exam, and so it was printed in black and white. So I could barely understand what was on it anyway. But they basically showed you this thing that looked like a microscopic scan with circles, and then it told you that these were cement minerals or something related to the materials, right? And you had to guess what it was. Not guess, but you had to label what it was. Okay? You had to label what I was guessing. You had to label what it was. The only way you could know for sure what it was by looking at the scale. because in the bottom right hand picture, the bottom right hand side of that picture, there was a scale. That's the only way you could tell whether you were looking at molecules, or you were looking at atoms, or you're looking at, because like when we walked out of the exam, one of my friends was like, bro, I got it, man. It was like the fine aggregate and then the coarse aggregate, and then the other dude was like, what are you talking about? It's carbon, and it's like, you get what I mean? Like, because the size is completely different. You wouldn't know. The only way you would know is by knowing what size, what scale you're looking at. Like if you're looking at, like if it's elements, then it has to be like a certain scale. If it's aggregate, it's a certain scale, right? There's a long-winded way of saying it. Just like have an idea as to how big these things are, and I think it's fine. Right.
Yeah, I agree with Prash. The materials part of the course is the stupidest part of the course, but week 5 is the hardest part of the course. So once you get over that hurdle, it should be.
By the way, the materials is also the trickiest part of the course because it's like Taewan's like that's his jam. Because he's he's a materials person. That's his main research area is materials. So I've often noticed that the calcs are not super like they're not out to get you. Materials side will be out to get you.
All right, round of applause for Will and thanks again. Thanks for your time.